In the vastness of the cosmos, where galaxies blaze and black holes devour stars, there exists nothing. A place so empty, so impossibly cold, that even the cosmic microwave background, the lingering afterglow of the Big Bang, seems to vanish. Deep within the constellation Eridanus lies a shadow, a supervoid spanning over 1 billion light years. No stars, no galaxies, no light, just absence. But this isn't just an astronomical oddity. Something about this void defies what we thought we knew about the universe's structure, and maybe, just maybe, about reality itself. What could possibly be hiding in a place so cold, even light avoids it? Subscribe if you believe the universe still keeps secrets, and join us as we descend into the most chilling, perplexing mystery ever recorded in space. The cold spot of Eridanus. There are places in the universe where light is devoured, where gravity crushes even photons into silence. Black holes, neutron stars, the jagged cores of collapsing galaxies. But this was something else. In 2004, data streamed in from one of NASA's most ambitious projects, the Wilkinson Microwave Anisotropy Probe, or WMAP. Its mission: to map the infant glow of the universe, the cosmic microwave background, the faded radiation left over from the Big Bang. Think of it as a baby photo of the cosmos, taken just 380,000 years after its birth. The image was expected to be gently mottled, dotted with warm and cool patches. Nothing surprising, but somewhere in the southern hemisphere of the sky, the signal dipped sharply, unexpectedly, a chilling blue blotch in the direction of the constellation Eridanus. It was unlike anything else in the map. Not just cold, eerily cold, not just different, anomalous. They called it the cold spot. At first, scientists were skeptical. Surely this was a data artifact, a processing error, a smudge on the cosmic lens. But no matter how they reran the algorithms or refined the instruments, the anomaly remained, staring back at them like an open wound in the sky. It was too large, too cold, and far too consistent to be noise. Some dismissed it as a statistical fluke, a 1 in 100 chance occurrence in the randomness of the early universe. But others weren't so quick to look away, because the more they stared into the cold spot, the more it stared back. A team led by Dr. Lawrence Rudnick at the University of Minnesota took it further. They compared the cold spot's location with massive galaxy surveys. What they found chilled them more than the temperature reading itself. In that direction of space, there seemed to be a staggering absence of galaxies, a gap that spanned nearly 1 billion light years. This wasn't just a cold patch in temperature. It was a hole in structure, a cosmic desert, a true supervoid. Now, imagine this. You're looking out across an ocean, expecting a horizon of stars. But instead, you find a pitch-black trench, where even starlight seems to thin and dissolve. That was the cold spot. And if the universe is a fabric, then this was a tear. But what could cause a void like this? According to the standard model of cosmology, the framework that describes how the universe evolved from the Big Bang, such a large and empty region shouldn't exist. Voids, yes, cosmic gaps between filaments of galaxies, absolutely, but not on this scale, not with this level of emptiness. The probability of a void this large occurring naturally, less than 1 in 100,000, and yet it's there, like a fingerprint burned into the universe, too precise to be an accident, too persistent to ignore. So what is it? a side effect of cosmic inflation, a gravitational anomaly, or something far stranger, a sign that our universe isn't as alone as we thought. As the cold spot gained attention, so too did the debates. Some argued it was a cold spot in temperature only, a statistical quirk, no more significant than a face in the clouds. Others believed it might be the first real evidence of something outside our universe interacting with it, a whisper from a neighboring reality. And here's where the story begins to spiral outward, like a ripple through space-time. Because if this cold spot isn't a coincidence, then everything we know about the large-scale structure of the universe could be wrong. One cosmologist put it bluntly, we have never seen anything like it. If it's real, it changes everything. Let's pause for a second, take a breath, look up at the night sky. Imagine every star, every galaxy you can see. Now imagine a hole so big, so cold, it could swallow all of it and still be hungry. What would you feel standing at the edge of that void? Awe, fear, wonder, because that's where we are, teetering at the edge of understanding, staring into something so vast and so silent that even our best theories barely dare to touch it. And this is just the beginning. As more powerful telescopes were aimed at this anomaly, what they uncovered was more disturbing than anyone expected. This wasn't just a cold spot in the sky. It was the start of a cosmic mystery that would challenge physics, stir imaginations, and force us to confront one of the oldest human fears, the fear of the unknown. Something is out there, and in the next chapter, we'll follow that trail deeper, into the stars, to the constellation where the cold spot resides, a place named after a river that flowed through the underworld. If the cold spot is a scar, then its coordinates form the bruise, a wound mapped onto a region of the sky that ancient astronomers once called Eridanus, the celestial river. In Greek myth, it was a river of the dead flowing through the underworld. Beneath the world of the living, a name meant for poetry or prophecy. Modern science hadn't paid much special attention to this patch of the cosmos until the cold spot demanded it. Now, Eridanus was under the spotlight, or rather, the absence of it, because something about this place was deeply, eerily wrong. It wasn't just colder in the microwave spectrum, it was emptier. When astronomers aimed radio telescopes, infrared sensors, and deep sky mapping tools toward Eridanus, they weren't just looking for heat. They were looking for structure, galaxies, dust, hydrogen, anything. What they found was less than nothing, a staggering absence, a supervoid, stretching over 1 billion light-years in diameter. Not just fewer galaxies, almost no galaxies at all. A cosmic desert with fewer than 20% of the expected mass distribution. It's like walking into a forest expecting trees, and instead finding a crater the size of a continent. To understand how bizarre this is, we need to talk about the cosmic web. The large-scale structure of the universe is a tangle of filaments, threads of galaxies and matter stretched across space, intersecting at nodes of gravitational attraction. Between these threads lie voids, relatively empty regions, where galaxies are sparse. These voids are common, but this void, the Eridanus supervoid, is different. It's not just big, it's too big, too symmetrical, too cold. It breaks the rules, even in simulations of the early universe. Chaotic, random, and inflating rapidly, voids of this size should be incredibly rare. Some researchers, like Dr. Istvan Shapudi, estimate the statistical probability of such a structure forming naturally at less than 0.0001%. It's like flipping a coin and getting heads 20 times in a row. 3 times in a row, which raises the unsettling question: is something actively repelling matter in this region? Let's visualize that. Imagine the universe as the surface of a still lake, rippling gently with matter and energy after the Big Bang. Then suddenly, a region where the ripples vanish. No waves, no motion, just stillness. As if something pressed down and erased the pattern. That's what aridness looks like. And here's the thing. Galaxies don't just fail to form there. They move away from it. Studies of galactic velocities show subtle deviations, as if something invisible is pushing matter outward. Not gravity pulling, but an unseen hand pushing. A cosmic repulsion. Is this the result of exotic physics? A fluctuation in dark energy? Or could it be the sign of interaction, an imprint left behind by something beyond the observable universe? Some scientists speculate this could be the gravitational echo of a colliding universe. A neighbor, brushing up against ours during the inflationary period of the early cosmos, like 2 bubbles expanding in foam, touching, merging, or bouncing off each other. If so, iridness may be the bruise. That idea might sound speculative, even wild. But here's the twist. The cold spot matches. Certain models predicted before the cold spot was even discovered. Dr. Laura, for example, predicted that if our universe had interacted with others, it would leave signs in the CMB. Cold spots, voids, distortions in density. Then the cold spot was found. Coincidence or evidence? And now the focus sharpens. Not just on the cold spot, but the place that hosts it. Iridness has become the stage, a place of myth and mystery, now turned into a scientific crucible. What once was a name in a star chart is now the eye of a storm in cosmological theory, and what's most disturbing and beautiful is that we don't know what's at the center of it. There could be nothing, truly nothing, or there could be something, an undiscovered law, an ancient interaction, a fold in space, or even, as some suggest, a gravitational pocket left behind by a failed universe. The question echoes, can emptiness be created, or must it be caused? The human story weaves through this mystery too. The researchers scanning thousands of galaxies by hand, the graduate students questioning their mentors, the lone theorists publishing risky papers, daring to link the cold spot with something beyond known physics, knowing full well the ridicule that often follows such claims. One astronomer wrote in her notes, "We expect the universe to make sense. This place refuses to." And as the map of aridness grows clearer, the puzzle grows deeper. In the next chapter, we'll leave the structure behind and focus on the light itself, because what's even more terrifying than a place without stars is what happens to the few rays of light that dare to pass through it. They stretch, they fade, they die. Light is the one constant the universe has always promised us. From the glow of a nearby candle to the aftershock of the Big Bang, light connects everything. It's our messenger, our timeline, the ancient code that tells us what the cosmos was, doing billions of years ago. But when that light passes through the aridness, something happens. It begins to fade, stretched, thinned, distorted, not simply dimmed by distance, but sapped, as if the void itself is draining its energy. A phenomenon known as the integrated Sachs-Wolf effect. Normally, photons gain a little energy when they fall into a gravitational well and lose it climbing back out. But in a universe dominated by dark energy, expanding at an accelerating rate, those gravitational wells stretch while the light is still inside. and in rare cases, like the cold spot, this can lead to a permanent net energy loss. To put it simply, light enters the void hole, but exits a ghost. This discovery wasn't made lightly. It came from years of painstaking work led by scientists like Dr. Istvan Shapaddy and his team at the University of Hawaii. In 2015, using data from the Dark Energy Survey and WISE, the Wide Field Infrared Survey Explorer, they detected a significant dip in galaxy density in the Eridanus region. The correlation between that supervoid and the CMB cold spot was no longer theoretical. There it was, a billion light-year wide void, visibly affecting the photons that passed through it. Imagine that, a stretch of space so vast and so empty. It starves light on its journey through time. But there's more. This isn't just a temperature effect. It's not a mere gravitational hiccup. Some photons appear to lose coherence. Patterns in light polarization, angular momentum, and redshift values begin to warp, not just bend, but twist in subtle, inexplicable ways. It's as if the void is not a passive region, but an active filter. Some theorists speculate it may be interacting with quantum vacuum fluctuations, the restless dance of particles that flicker in and out of existence in supposedly empty space. In most of the universe, these fluctuations cancel out. But what if, inside the void, something disturbs that balance? Could this place be a kind of quantum sink? A region where vacuum energy, the very heartbeat of space-time, behaves differently? That might explain the light loss. It might also hint at something far stranger, that the void is not just a space between things, but a thing in itself, a kind of structure, a bubble, a scar. Some physicists have proposed that the Eridanus void could be the remnant of a topological defect, a misalignment in space-time left over from the universe's earliest moments. Picture the universe as a quilt stretching rapidly after the Big Bang. If two patches stitched together with different settings, different vacuum states, touched, they could create a fault line, a region where the rules break down, where light can't behave the way it does elsewhere. In theoretical models, these are called domain walls, boundaries between regions of the universe that settled into different states of reality. They're rare, and they shouldn't exist anymore. But if one did survive, if one still does, then the Eridanus cold spot might not just be a void. It might be a wall between us and something else. What would that mean? It could mean photons aren't simply dying there, they're changing, being altered in subtle, unknown ways as they cross from one vacuum state to another. Not destroyed, but rewritten. It raises a haunting possibility. What if we're misreading the light that reaches us from beyond the void? What if galaxies on the far side look dim or shifted, not because they are far away, but because they're behind a veil? That would mean the universe is not as it appears, that distances are distorted, that maps are flawed, that what we think is a boundary might actually be a lens made not of glass, but of gravity, of warped time, a bubble through which light must whisper, distorted and incomplete. And here's the most chilling part. Some photons don't come out at all. Surveys show a statistical underdensity of light from galaxies behind the cold spot, not just dimmer, missing, lost, as if the void doesn't just stretch light, it erases it. Where do those photons go? Is it possible that the void redirects them, absorbs them? Or is there another side entirely unreachable from here? We don't know, not yet, but the very idea that there's a place in the universe where light goes to die is both terrifying and deeply compelling. Because light is more than a wave, more than a particle. It's information, and if information can be erased, what else can be? Next, we'll widen our lens, zoom out, because Eridanus isn't the only supervoid in the universe, but none are. Quite like this. So are these immense cosmic gaps just accidents of expansion, or are they ... clues? We'll ask the question no one wants to ask. Are voids just what's left behind, or are they meant to be there? The universe is not uniform. From a distance, it may appear like a smooth black canvas speckled with stars, but zoom out far enough, and a different pattern emerges, like threads in a spider's web or neural pathways in a vast mind. Galaxies cluster into filaments and walls, while the spaces in between the voids stretch like hollows in the cosmic sponge. These voids are natural, expected. They're part of how matter organizes itself after the Big Bang, expanding and cooling, guided by the pull of gravity and the push of dark energy. Most are hundreds of millions of light years across immense, yes, but statistically predictable, but not the cold spot. The Eridanus void is different. It's too big, too empty, too aligned with the cold spot in the cosmic microwave background to be dismissed as coincidence. And so we must ask, are supervoids just statistical quirks in a chaotic cosmos, or are they something more, something like fingerprints, clues, evidence of forces we don't yet understand? In 2007, a controversial paper shook the astrophysics world. Dr. Laura Mersini Houghton, a theoretical physicist at the University of North Carolina, suggested that the cold spot might be the result of a collision, not between galaxies or stars, but between universes. According to her theory, during the inflationary phase of the early universe, when space expanded faster than the speed of light, our universe may have bumped into another, separate bubble of reality. The result? A scar, a ripple, a disturbance in the distribution of matter and temperature. A cold spot at first. This idea seemed outrageous. The multiverse, bumping bubbles. It sounded like science fiction, but the predictions matched the data too well to ignore. The cold spot, she argued, was exactly the kind of imprint a neighboring universe would leave if it came too close during inflation. Not just a cold area, but a voided area where matter thinned and light dimmed. Could the Eridanus void be the echo of that collision? We don't know for sure, but it forced scientists to re-examine other voids. Are there more cold spots out there? A team at Durham University developed simulations using the lambda-CDM model, our best approximation of cosmic evolution. These simulations generated thousands of artificial universes, each filled with galaxies, voids, and filaments. In nearly every case, voids as large and deep as Eridanus failed to form naturally. Out of thousands of simulated skies, only a handful showed anything remotely close. That's when a deeper truth began to emerge. Most supervoids are not symmetrical. They're irregular, messy, chaotic. But the Eridanus void, it's clean, spherical, almost deliberate. Could nature form such a shape on its own? Or is it shaped by something? That's what keeps researchers up at night. Some believe it could be a region of exotic physics, where dark energy behaves differently, or where space-time itself has a different curvature. Others believe it could be the last remnant of a quantum fluctuation that failed to generate structure, a place where the seeds of galaxies simply never formed. But there's another possibility, one far more speculative, one that lingers just beyond the edges of current science? What if the void is not the result of missing matter, but of repelled matter? Picture a balloon covered in dust. Now imagine that in one spot, something pushes the dust away from within, not pulling matter in like a black hole, but repelling it outward. That's what some physicists have proposed, that the void could be created by a repulsive gravitational field, a region of negative energy density, something that bends space, not inward, but outward. This flips everything we know about gravity on its head. It would mean that something exists inside the void that's not just empty, it's anti-structure, not nothingness, but the active absence of something, like a bubble of rejection in the fabric of space. A few researchers, such as Dr. Istvan Shapudi and collaborators, are even exploring the possibility that large-scale voids like this may act as dark energy sinks, amplifying the universe's expansion in those regions. If so, it means that the cold spot may be accelerating faster than the rest of the universe, growing colder, emptier, more detached with time. And if that's true, what happens when these regions grow large enough to affect surrounding space? What happens when the void expands? Could the cold spot be a kind of cosmic cancer? Not malicious, but unstoppable. An expanding region where physics itself behaves differently, slowly devouring structure, thinning reality like ice melting beneath your feet. Or is it something even older, a remnant from before our universe solidified into its current state? A leftover, a fossil, a place where the rules never settled. That's the beauty and terror of supervoids. They ask us to confront a question most models quietly sidestep. Is our universe uniform, or only pretending to be? And so we keep searching, comparing voids, running simulations, looking for patterns in the chaos. But none, so far, are quite like the cold spot. And if it truly is a clue, then it's pointing somewhere profound, because next we step beyond physics as we know it, into the shimmering edge of possibility, into a theory once laughed out of lecture halls and now whispered in conferences, the multiverse. What if we're not looking into a void, but through it, into another reality entirely? The night sky has always whispered that there might be more worlds, more wonders, more places than our minds can hold. But what if more means not just more stars and galaxies, but more universes? Universes with different laws of physics, different histories, different versions of reality, entire cosmic bubbles expanding in the darkness beyond our own. This is the multiverse hypothesis, a frontier so strange and exhilarating that even its name sounds like a dare. But how did a wound in our sky, the cold spot, become a suspect in this grandest of mysteries? Let's step back. In the earliest fraction of a second after the Big Bang, our universe experienced something called inflation, an explosion not of matter, but of space itself. Imagine a balloon inflating so rapidly that the dots on its surface spread beyond sight in the blink of an eye. Quantum fluctuations, tiny uncertainties in energy, were blown up to cosmic scales, planting the seeds for galaxies and voids that leading theorists like Andre Linde, Max Tegmark, and Laura Mersina Houghton have asked, what if inflation didn't just create our universe, but countless others? Each a bubble, each born from quantum randomness, expanding in a foamy, ever-branching sea. If so, most bubbles would forever remain isolated, sealed off by the relentless swelling of space. But what if, sometimes, bubbles touched? What if, at the fringes, two universes brushed like ripples, meeting in a pond, and left a mark where their boundaries collided? Mercini Horton and her colleagues predicted with uncanny precision that such a collision would leave behind a cold spot in the cosmic microwave background. Not just any cold spot, but one with a specific size and temperature that would later be observed in Eridna. A fingerprint of another universe pressing against ours in its infancy. This isn't fantasy, it's mathematical possibility. The multiverse is baked into the equations of cosmic inflation. It's a logical extension of quantum mechanics. And now, perhaps, it's scrawled across our own sky. But what would it mean if it were true? Picture it, two universes, each with their own physics, each a realm of possibility, colliding at the speed of light. In the collision zone, energy could be lost, matter scattered, the very texture of space bruised and altered. Our universe might carry scars, not just the cold spot, but other oddities, other anomalies waiting to be noticed. This possibility has electrified and divided the scientific community. Some physicists, like Max Tegmark, embrace the logic. If inflation can happen once, why not everywhere? Others, more skeptical, warned that extraordinary claims demand extraordinary evidence. After all, we can't step outside our universe and peer in. We can only read the signs. But the cold spot is a sign. Its size, its symmetry, its sheer improbability, all hint at something beyond random chance. And the idea that it could be a multiversal bruise is no longer just a fringe speculation. It's a viable hypothesis, tested with real data, argued in the pages of the world's top journals. So, how could we ever know for sure? Is it possible to prove the multiverse, to glimpse the worlds beyond our own? The search is on. Physicists run simulations of bubble collisions, searching for patterns that match what we see. They comb the cosmic microwave background for other cold spots, other hints of contact. They debate whether the fundamental constants of nature, the mass of the electron, the strength of gravity, could be explained if we are just one random outcome among countless possible worlds. But the evidence is subtle, slippery, shrouded in the randomness of quantum birth. For every scientist convinced that the cold spot is a multiversal message, another cautions that our understanding of voids, of cosmic structure, is far from complete. Still, the narrative has changed, where once the universe felt infinite and alone, now it feels like a room in a vast mansion. Some rooms locked, some open, some so different that their inhabitants would never recognize ours as real. And so, we're left with a question that crackles with both fear and hope. If the multiverse exists, what else might be out there? Worlds with different histories, doppelgangers of ourselves, laws of physics we could barely imagine. This is not just a scientific question, it's a human one. It's about loneliness and connection, about the possibility that our universe, for all its vastness, is only a small part of something grander and stranger than we ever dreamed. And now, with every new observation, with every whisper from the cold spot, we are drawn deeper into this cosmic riddle. The next chapter will follow the growing web of evidence, because the cold spot may not be the only scar. There may be others, shadows of collisions, echoes of universes touching, written into the sky. And if so, we must ask, how many times has our universe been struck by what lies beyond? And what happens if it happens again? It's easy to imagine the universe as a serene and silent expanse, unchanging but for the slow dance of galaxies and the gentle ripples of time. But what if the cosmos is haunted by collisions, its surface marked by encounters so rare and profound? that their echoes linger for billions of years? What if the cold spot is not a solitary bruise, but just one of many scars left by the universe's turbulent past, the shadows of other realms pressed into our own? As the multiverse hypothesis gained traction, physicists and cosmologists began to search for more cold spots, more anomalies, more evidence that our universe is not an isolated bubble, but a participant in a much larger cosmic drama. Supercomputers hummed with simulations, weaving digital universes with millions of possible outcomes. When two bubbles of reality collide, in these models, the aftermath is both predictable and surreal. There's a temperature dip, a cold zone ringed by subtle distortions. Matter thins, patterns in the cosmic microwave background twist. Sometimes, new anomalies appear, arcs, rings, or multiple cold patches, each with a story to tell. Researchers pored over the real sky, mapping the cosmic microwave background in finer and finer detail. The Planck satellite, launched by the European Space Agency, became their window to the universe's baby picture, and perhaps to its interdimensional secrets. And as the data accumulated, faint hints began to emerge. Was there a strange ring around the cold spot? Were there smaller, colder regions dotted elsewhere, too consistent to be mere chance? Some patterns seemed to match the theoretical models for interuniversal collisions. A ghostly fingerprint from a neighbor universe brushing against ours. Yet each discovery brought new questions. If collisions happened once, could they happen again? Are we surrounded by subtle scars, each the memory of a cosmic encounter? For Dr. Hiranya Peiris and her team at University College London, this search became a quest. She recalls late nights sifting through pixelated maps, hunting for the improbable. Each anomaly could be a statistical blip, or the sign of something profound. It's the difference between noise and music, chaos and message. But the universe is a master of camouflage. For every anomaly, there is a chorus of skeptics ready to explain it away. Foreground contamination, instrumental error, statistical flukes. The sky is noisy, after all. Cosmic microwave background radiation is famously lumpy, random, chaotic, hard to decipher. Yet doubt is part of the scientific process. It keeps the search honest. The possibility of error makes the prospect of truth even more exhilarating. Viewers, imagine standing on a high plateau beneath the night sky, knowing that what looks like empty darkness might be the canvas of a hidden story. If you had the power to peel back the fabric of space, what might you find? Could you spot the difference between a scar and a birthmark, between a random void and a message left by another world? As the simulations grew more sophisticated, something intriguing happened. The characteristics of the cold spot, its shape and temperature, matched those of a universe-to-universe collision. But there was a catch. There were not as many such marks as the models predicted. If collisions were common, the sky should be full of them. Yet the cold spot remained exceptional. Was this a sign that our universe has had only one encounter? Or are we missing something, failing to recognize other scars because they take on different forms? A hotspot here, a subtle wave there, a region of unexplained symmetry or emptiness. This mystery has led some to speculate that the cold spot is not just a random anomaly, but a unique intersection, a place where the veil between universes is thinnest, and the shadows of other realms leak through. If that's the case, what else might slip across? Could gravity, particles, or even information pass between universes? Theoretical physics hints at the possibility, though it remains far from proven. But the search continues, growing more creative and ambitious. New telescopes scan the sky, not just for galaxies, but for patterns, circular features, temperature gradients, gravitational anomalies. Physicists invent ever bolder tests, knowing that any real signal will be subtle, almost lost in the static. Still, the idea persists, haunting the field. What if the cold spot is just the beginning? What if all along we have been living in the aftermath of a cosmic collision, the children of a universe marked by encounters we cannot see, only feel? What if the next scar is yet to be discovered, waiting for a new generation of scientists to recognize its shape? Perhaps you, watching this now, are among them. Maybe your imagination, your questions, will help shape the next great discovery. In our next chapter, we travel back to the dawn of time, to the cosmic microwave background itself, and the secrets it holds. Because if the cold spot is a message, then the universe's oldest light might be the code. Is there meaning in the static? A whisper from the ancient past, or just more noise? If you could travel back in time, not just centuries or millennia, but almost 14 billion years to the moment when the cosmos took its first breath, what would you see? There'd be no galaxies, no stars, not even atoms as we know them. Instead, you'd witness a universe so dense, so hot, that light itself was trapped, bouncing endlessly off charged particles. Then, in a flash-cold recombination, the universe cooled enough for atoms to form. Light, for the first time, was free. That ancient light is the cosmic microwave background, the CMB. It's the oldest signal we can observe. A faint glow stretched by time and expansion, now cold and ghostly at just 2.7 degrees above absolute zero. Yet within this whisper of the Big Bang, there are secret ripples, scars, and shadows that reveal how our universe began. Mapping the CMB is like taking the universe's baby photos. Every patch, every subtle fluctuation encodes the primordial soup's density, temperature, and even the seeds of future galaxies. The patterns are complex, but mostly as expected, a cosmic lottery of warm and cool spots. No one area too unusual, except for one, the cold spot. At first, it was just a curiosity. The 2003 WMAP mission detected it, but the team hesitated. Was this just random statistical noise? The universe, after all, is messy. But subsequent missions, most notably East Planck satellite, confirmed its existence. The cold spot wasn't an artifact. It was real. Stubbornly, there a vast blue wound, colder by about 70 microkelvin than the surrounding sky. Insignificant in terms of absolute temperature, but in cosmological terms, a shattering anomaly. What does this mean? In the standard cosmological model, the temperature variations in the CMB should reflect small, random differences in density in the early universe. These variations are the seeds from which all structure stars, galaxies, clusters eventually grew. But the cold spot, it doesn't fit. Its size, its depth, its singularity, none of it matches what we'd expect from quantum randomness alone. Some theorists have tried to explain it with statistics. Maybe it's just an incredibly rare coincidence, a 1 in 100,000 outlier, but as the data piles up, that explanation feels less and less convincing. Why should such a vast, coherent, cold region exist in a universe otherwise so well behaved? Other scientists turn to cosmic inflation, searching for answers in the split second after the Big Bang. If inflation was lumpy, If the quantum fields that powered it fluctuated in just the right way, could a supervoid be born, a region where matter is thin, where light loses energy, and the CMB appears colder? It's possible, but the odds are daunting. The cold spot's precise alignment with the Eridanus supervoid only deepens the puzzle. Enter a new generation of researchers, armed with more powerful tools and fresher perspectives. Dr. Joanna Dunkley, an expert in CMB analysis, describes the challenge. We're sifting through the noise of the early universe, looking for a message that may not want to be found. Every tiny fluctuation is a clue, but also a distraction. One possibility that haunts the field is the cold spot, a message from before our universe even began. Some cosmologists believe it could be the signature of a bubble universe colliding with our own, written into the CMB as a faint but indelible marker. Cosmic telegram from a neighbor we'll never meet. Others suggest more subtle origins, a primordial black hole that evaporated, leaving a shadow in the afterglow, a knot in the cosmic web that grew from a unique fluctuation, or even a brief breakdown in the laws of physics themselves. But perhaps the most profound implication is this: the cold spot could be a glimpse into the universe's memory, a place where history is recorded not in atoms or galaxies, but in the very temperature of space. If so, the CMB is more than a relic. It's a living archive, a record that spans almost all of time. This is where the science blurs into philosophy. If the CMB is a cosmic photograph, what else might it reveal if we learn to read it more closely? Are there other messages, other anomalies waiting in the static? Are we, in some strange way, looking not just at the past, but at a layer of reality where time and space still hold secrets too vast for us to grasp? And so, scientists keep listening, keep mapping, keep searching for meaning in the hum of the oldest light. The cold spot endures, daring us to decode its story. Next, we'll meet the explorers who walk the map's edge, thus who risk careers and reputations to chase the universe's strangest clues. The human element in a cosmic story, because when you stare into the void stares back, and sometimes it calls your name. The universe rewards those willing to walk its edge. These are the void walkers, scientists, dreamers, skeptics, and risk-takers who devote their lives to exploring cosmic absences. Not content to merely catalogue the shining galaxies, they hunt for the places where almost nothing remains. Because sometimes, what's missing tells a deeper story than what is present. To map the Eridanus void and the mystery of the cold spot, a new generation of explorers assembled from every corner of the world. Some, like Dr. Istvan in Hawaii, stare into digital voids late into the night, running galaxy surveys until patterns emerge from apparent randomness. Others, like Dr. Eliseel Dobos in Hungary, build cosmic web simulations that stretch the very limits of supercomputing power. Their data pours in from a symphony of instruments, the dark energy surveys, sensitive telescopes in Chile, the wide-field infrared survey explorer orbiting above Earth, even radio dishes spanning continents. Each piece of equipment brings the void into sharper focus. These void walkers chase phantoms across a cosmic lattice. They seek not only emptiness, but the subtle fingerprints it leaves on the universe's fabric, gravitational lensing, where no galaxy bends the light, weak signals in the radio spectrum, temperature dips that persist against all odds. Their tools are precise, but their quarry is elusive. After all, how do you find what isn't there? There are human stories woven through every cold calculation. Graduate students working endless nights, unsure if their effort will ever matter. Veteran astronomers who bet entire careers on finding meaning in a dataset that most consider a cosmic fluke. Some become obsessed, following every lead. Others grow weary, feeling the weight of skepticism from their peers. Still, a few persist, driven by the sense that the universe is daring them to notice something everyone else missed. One such moment came in 2015. Dr. Shapudi's team, after years of mapping millions of galaxies, published evidence that the cold spot was indeed aligned with a supervoid, the largest ever found. The news made waves, but it was met with as much criticism as praise. The supervoid, they argued, wasn't quite empty enough to explain the cold spot's depth. Was it real, or just the universe's way of playing tricks with probability? The void walkers pressed on, using innovative techniques to refine their searches. Dr. Dobos and collaborators applied machine learning to scan for voids in galaxy surveys, training algorithms to detect shapes and patterns the human eye would miss. This marriage of human curiosity and artificial intelligence became essential. The universe is vast, and human intuition alone cannot keep up with its scale. Meanwhile, new surveys like the Sloan Digital Sky Survey and the Vesta Hemisphere Survey began to fill in the map, revealing not just one void, but a tapestry of hollows, some shallow, some deep, some unexpectedly symmetrical. And still, Eridanus stood out, larger and colder than the rest. Fieldwork also played its part. Teams trekked to mountaintop observatories in Chile and the Canary Islands, enduring harsh climates and lonely nights to calibrate their telescopes and verify remote data. Every clear night, they aimed their lenses at empty space, recording the silence, hoping that in the darkness they might catch a glimpse of a missing galaxy, a subtle lensing arc, or even a new cold anomaly. But mapping the unknown is not just about gathering data. It's about asking dangerous questions. What if our models are wrong? What if the universe is hiding something in plain sight? What if the rules we use to decode cosmic structure are themselves incomplete? This quest takes its toll. Funding is uncertain. Reputations are at stake. The risk of spending years in pursuit of a ghost is real, yet many are undeterred. As Dr. Shapudi once confessed in a quiet interview, it's a kind of obsession. The void stares back at you. It's always asking, what if you're right? Interactive moment. If you were on this journey, staring at billions of data points, would you trust the numbers or your instincts? Would you risk ridicule to pursue an answer that no one else believes in? For the Voidwalkers, every new observation is a small victory. Each confirmed absence, each sharper boundary, each measurement that hints at a deeper reality. These are their rewards. Their legacy, perhaps, will be to show us that emptiness is not meaningless, but a canvas for the universe's greatest mysteries. Yet with each new void discovered, the Eridanus mystery only deepens. For all the mapping, all the data, one question remains unanswered. Is this just the universe's luck of the draw, or a sign that something profound, even terrifying, lies beneath the surface? In our next chapter, we'll peer into the heart of cosmic emptiness and wonder. What force could carve a void so vast? Is this the playground of dark energy, where the very laws of expansion may break free from our expectations? When you map the unknown, sometimes the map changes you. There is a force at work in the cosmos, more mysterious than gravity, more powerful than the light from a trillion suns. It is everywhere and nowhere a silent, invisible pressure that accelerates the universe's expansion. Astronomers call it dark energy, and its nature is one of the deepest enigmas of modern science. If the cold spot is a cosmic wound, then dark energy may be the unseen hand that keeps that wound from ever closing. In the late 1990s, two rival teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were racing to measure the expansion of the universe. Their supernova data delivered a shock. The cosmos was not slowing down, but speeding up. Something was counteracting gravity, making space itself balloon faster and faster. That something became known as dark energy. It now makes up about 70% of all the energy in the universe, yet we have no idea what it truly is. But what if dark energy doesn't just expand the universe as a whole? What if, in certain places, it behaves differently, concentrating, fluctuating, even growing stronger? This possibility has become a focus for those seeking to explain the cold spot and its accompanying void. Could the Eridanus supervoid be a playground for dark energy, a laboratory where its effects are written large on the fabric of space? Some cosmologists propose that the void is not merely a region of absence, but a bubble where dark energy has a local overdensity. In simple terms, imagine space itself swelling more rapidly inside the void, pushing galaxies outward and thinning matter to the breaking point. In these models, the integrated Sachs-Wolf effect, the process by which photons lose energy as they traverse the expanding void, would be magnified. Light would stretch, fade, and vanish more dramatically than anywhere else. Dr. Alexander Kashlinsky, a cosmologist at NASA, has called these regions repulsion zones. In such places, gravity is outgunned, and the normal flow of cosmic matter reverses. Instead of being drawn inward, galaxies drift outward, carried by the relentless surge of space itself. This has terrifying implications. If dark energy is not perfectly uniform, if it can clump or vary in strength, then the fundamental architecture of the universe is less stable than we thought. The void could grow, expand, and eventually swallow neighboring regions, leaving behind only emptiness. It is as if the universe were riddled with hidden fissures, each one a seed of accelerated decay. Interactive moment. If dark energy could swell or recede unpredictably, what would it mean for our cosmic future? Would we find ourselves living in a shrinking island of matter, surrounded by growing oceans of nothing? And yet the evidence is subtle. Detecting the fingerprints of dark energy inside a void is an astronomical challenge. It requires precise measurements of galaxy velocities, CMB temperature shifts, and the faint gravitational tug of empty space. Teams like Dr. Shapudi's use the largest telescopes on Earth and data from satellites in orbit, piecing together a puzzle from the faintest of clues. Skeptics caution that other effects, statistical noise, variations in the cosmic web could mimic the signature of variable dark energy. But the cold spot, with its deep void and sharp boundaries, remains a compelling candidate. It's the right size, the right temperature, the right emptiness. If dark energy does fluctuate, the cold spot might be our first clear sign. The implications ripple outward. If dark energy can carve out a void on this scale, it could be responsible for other anomalies. From the mysterious dark flow, unexpected movement of galaxy clusters, to the great cosmic axis of evil, an alignment of temperature, anomalies across the sky. Each may be a side effect, a symptom of physics operating differently in pockets of space. But there's a philosophical question lurking beneath the science: is emptiness really empty? Or is it a field alive, dynamic, dangerous, where the rules of the universe can bend or even break? For the void walkers and theorists, the Eridanus region is more than a curiosity. It's a warning that the structure of the universe may not be as stable as we once hoped. That in the cosmic game, dark energy holds cards we have yet to see. And as we peer deeper into the playground of dark energy, a new mystery emerges on the horizon: cosmic force pushing galaxies away from a region not far from the cold spot. It's not just absence, but repulsion. Next, we meet the so-called Great Repeller, a force that dares to push against gravity itself. If dark energy can change, what else in the universe is more volatile than we ever dared to imagine? For centuries, humanity has assumed that gravity reigns supreme. Gravity binds us to Earth, holds the planets in orbit, gathers galaxies, and shapes the very fabric of space. Yet, as our telescopes grew sharper and our surveys more ambitious, a new and unsettling force appeared on the cosmic stage, a force that doesn't pull, but pushes. Astronomers call it the Great Repeller. The story begins with a puzzle. In the vastness of the universe, galaxies and clusters are not just randomly scattered. They flow, subtly drawn along invisible rivers of gravity. In the late 20th and early 21st centuries, scientists tracked the motions of thousands of galaxies, mapping their velocities and directions across the sky. The expectation was simple: galaxies should move toward regions with more mass, like the enormous Shapley supercluster pulled by the gravity of hundreds of thousands of suns. But that's not what the data revealed. Instead, galaxy clusters, our own local group, were moving in a direction that didn't quite add up. Their velocities couldn't be explained solely by gravitational attraction. Something seemed to be pushing against them from the other side of the universe, in a direction suspiciously close to the Eridanus void. In 2017, Dr. Yehuda Hoffman and his team published a groundbreaking paper describing a strange cosmic feature, the dipole repeller. Using data from galaxy flow surveys and computer models, they discovered a vast region of space, nearly devoid of galaxies, acting like a gravitational hole. Rather than pulling galaxies inward, it seemed to push them away, shaping the large-scale flow of matter in the local universe. This was a paradigm shift. While gravity gathers, the repeller disperses. Imagine a landscape where hills pull water downhill, but in one spot, an invisible force pushes water away, creating a dry basin. That's what the dipole repeller does. To galaxies, a gravitational vacuum, sending them flowing outward into denser regions. And where is this repeller? Not far from Eridanus, not far from the cold spot. Once again, the most profound mysteries seem to cluster in the same cosmic neighborhood. Some scientists suggest the repeller and the Eridanus void may be intimately linked to sides of the same phenomenon. Both are regions of profound emptiness. Both exert an unseen influence. Both break the conventional rules of cosmic structure. If the cold spot is a wound, the repeller may be the knife. But what could create such a force? Gravity, as described by Einstein, is always attractive. Yet, general relativity allows for negative mass solutions, exotic forms of matter or energy that repel rather than attract. While no such material has been confirmed, the mathematical possibility haunts the edges of theoretical physics. Perhaps the repeller is a vast region where dark energy dominates, pushing matter away more aggressively than elsewhere. Or perhaps it's the result of ancient quantum fluctuations, a leftover from inflation that never filled with galaxies, becoming a permanent scar on space-time. Dr. Hoffman describes the discovery with awe and humility. We expect the universe to pull together, not push apart. Finding a repeller forces us to rethink the architecture of the cosmos. It's as if the universe is telling us there are rules we haven't discovered yet. Interactive moment. Imagine if you were piloting a starship through space, and you encountered a region where, instead of being pulled in by gravity, you were gently but irresistibly pushed away. Would you keep going, or would you turn back, fearing what lay at the heart of such emptiness? The existence of the dipole repeller also casts new light on the dark flow phenomenon, the mysterious, high-speed motion of galaxy clusters across the universe, seemingly unaffected by local gravity. Could these enigmatic flows be the long-range effects of repulsive regions scattered across the cosmic web? Are there more repellers out there, hiding in the shadows, quietly shaping the fate of galaxies? And if so, what does that mean for our own cosmic neighborhood? Is our movement through the universe dictated not only by where mass accumulates, but also by where it is profoundly absent? Some theorists even speculate that repellers may mark the boundaries of our observable universe, hinting at structures, perhaps even other universes, beyond the reach of light. For now, the dipole repeller remains a mystery, an invisible hand guiding the motion of worlds. Its presence complicates our understanding, but also opens thrilling new avenues of inquiry, because in the end, every discovery that pushes us away from certainty pulls us closer to truth. Next, we return to the human story, a journey of awe, skepticism, and courage as we follow the scientists staring into the abyss, determined to solve the greatest cosmic riddle of our age. When the universe both pulls and pushes, who will dare to stand in the middle and ask why? When we talk about cosmic voids and cold scars on the map of the universe, it's easy to drift into abstraction, to speak of distances in billions of light years and energies beyond imagination. But at the center of every cosmic riddle are human beings, scientists, skeptics, dreamers who choose to look into the abyss, searching for meaning in what others might call nothing at all. Dr. Istvan Shapudi stands on the summit of Mauna Kea, Hawaii, the wind cold, the air thin. Behind him, the universe unfurls in every direction, oceans of stars, galaxies, and, somewhere out there, a vast and silent nothing. It is here that Shapudi and his team gathered data that would fuel years of debate and wonder. They didn't just stare at maps. They remade them back in 2015. Shapudi's group made headlines with a discovery that sent ripples through the astrophysics community. By overlaying deep-field galaxy maps with cosmic microwave background data from the Planck satellite, they revealed an extraordinary correlation: the Eridanus supervoida real structure. Not just a statistical phantom matched the position and size of the CMB cold spot almost perfectly. This was not just a patch of chilly pixels in the sky. It was a physical place, mapped by human effort, traced by millions of lines of code and decades of late-night calculations. The team worked through frustration and awe, nights punctuated by both doubt and revelation. Shapudi remembers the moment. Vividly, the map came together, and the void emerged. It was as if the universe had left a signature remark that said, "Something happened here." But science, like the cosmos, resists easy answers. For every discovery, there are skeptics. Other teams, like that of Dr. Seshadri Nadathar in the UK, ran independent analyses, probing the same void. Challenging the correlation: was the supervoid empty enough? Was it deep enough to account for the full coldness of the spot? Could the data be a tricker product of selection effects or statistical bias? Debate sharpened. Conferences buzzed with arguments, for every voice insisting that the cold spot was a cosmological oddity. Another pointed to the mounting evidence. This was the largest structure yet observed, a void so immense it bent the rules of cosmic probability. Human emotion ran high. Graduate students, once excited by the thrill of discovery, now felt the crushing weight of scrutiny. Senior scientists defended their results, standing firm against a rising tide of skepticism. This was more than a question of data was, a test of belief, a contest between possibility and doubt, and yet, beneath it all, a strange consensus began to form. The cold spot was real. The iridinous void was real. The correlation was too clear to ignore. One researcher confessed privately, "It's not the emptiness that's frightening, it's how intentional it feels. Like something happened there, something we don't yet understand, but what? A random fluctuation magnified by chance, the result of dark energy's strange dance, or the echo of a universe beyond our own? Or was it something new, entirely an emergent property of the cosmic web, a feature we were never supposed to find?" As the debate unfolded, the world watched. Popular science magazines carried the story. Forums and comment sections filled with speculation. What does it mean to find a scar in the universe so large that even the laws of physics hesitate to explain it? And what does it mean to keep looking, knowing you might never find an answer? Interactive moment. Imagine yourself at the summit of Mauna Kea, the cold biting at your cheeks, the sky impossibly dark and clear. Would you feel small, or would you feel just for a moment the pulse of discovery? Would you risk years, even decades, for a chance to glimpse the unknown? These are not just technical questions, they are existential. Every step further into the abyss is a step into our own curiosity, our own hunger for meaning. As more data comes in, better telescopes, deeper surveys, AI-driven analysis, the iridinous mystery only grows. The void, mapped more clearly than ever, becomes both more familiar and more unfathomable. The scientists, human and fallible, become the bridge between numbers and wonder, and still the abyss stares back. The cold spot endures, silent as ever, daring us to keep searching, keep asking, keep dreaming. In the next chapter, we'll look at the strangest possibility of all. Could this cosmic wound be a glitch not in the universe, but in reality itself? Is the cold spot a flaw in the code of the cosmos? Perhaps the greatest mysteries are those that force us to see ourselves searching, uncertain, alive in the darkness. What if the cold spot isn't a product of ancient physics or cosmic collisions? What if instead it's something stranger, a flaw, not in the universe itself, but in the fabric of reality? This is the provocative idea some scientists, philosophers, and even computer engineers have begun to whisper. What if our universe is not ultimate reality, but a simulation, and the cold spot is a glitch in the cosmic code? To most, the idea sounds like science fiction, but in recent years, simulation theory has earned a surprising degree of serious consideration. Oxford philosopher Nick Bostrom and physicists like Silas Bean have wondered if a sufficiently advanced civilization could create a virtual universe with conscious beings inside. What's to stop them? And if they did, would the residents of that simulation ever notice the seams? The cold spot, with its improbable size, symmetry, and persistence, is precisely the kind of artifact that a simulation might produce. Think of a video game world flawless from a distance, But as you approach the edge, strange patterns emerge. Polygons stretch, textures flicker, the rules break down. The cold spot feels like a cosmic version of that patch of reality where the usual algorithms falter and something leaks through. Dr. Sabine Hosenfelder, a physicist and popular science communicator, summarizes the tension. We trust our theories because they work, but if reality is computed, there will be bugs. Maybe the cold spot is just that, a place where the code stutters. Skeptics of the simulation hypothesis argue that it's untestably metaphysical escape hatch, not a scientific theory. But some researchers push back, arguing that a simulated universe might contain specific, detectable patterns, mathematical regularities, unexplained anomalies, digital artifacts buried in the noise. The cold spot, with its singular strangeness, often sits at the center of such debates. Could it be a rendering error, a patch of undersampled data in the universe's high-definition texture, or perhaps a necessary artifact like or a marker left by the creators, invisible to most, but glaring to those who know how to look? There are stranger ideas still. If our universe is computed, then perhaps regions of high complexity, like galaxy clusters, require more processing power. To save resources, a simulation might reduce detail in places where nothing much happens, vast voids, where life and complexity are rare. The Eridanus void, with its emptiness and its cold spot, could simply be a region where the simulation cuts corners, filling space with a kind of cosmic PLACEHOLDER interactive moment, if you knew, with certainty, that you lived in a simulation. Would you want to know? Would it change the meaning you find in your life, or would the beauty and mystery of the cosmos remain just as profound? It's not just idle speculation. Some physicists, like Zora Davudi at MIT, have proposed real-world tests, searching for pixelation in the energy levels of cosmic rays, or for unexplained correlations in the cosmic microwave background signatures of an underlying digital grid. So far, these searches have come up empty, but the possibility lingers, hovering like a ghost at the edge of science. The cold spot itself resists simple explanation. It doesn't act like a data artifact. Its presence is confirmed by multiple satellites and independent surveys. Yet, in its uniqueness, it persists, singular, haunting, unresolved. If it is a glitch, then it is a persistent one. If it's a message, what could it mean? Some philosophers have mused, perhaps the greatest mysteries in our universe are clues left for us to find. Perhaps, by staring into the cold spot, by refusing to look away from what doesn't make sense, we are participating in the very experiment our creators set in motion. Or maybe the universe is stranger than any simulation. Maybe the cold spot is a natural, if improbable, phenomenon. A feature, not a bug. Yet the simulation question remains part science, part philosophy, part existential dare. If the cold spot is a flaw in the code, then what else might we discover? If we keep looking, what other seams in the fabric of reality are waiting to be found? As we move forward, the theories only grow stranger, the possibilities darker. In the next chapter, we travel not to the edges of a simulation, but to the edges of time itself. Some believe the cold spot is not a glitch or a scar, but a fossil from before the Big Bang. If reality has a code, then somewhere, something must be writing it. Are we reading the lines, or just guessing at the gaps? Imagine a place so old, so primordial, that it predates the very universe we call home a shadow, not just in space, but in time itself? What if the cold spot is more than a cosmic coincidence, a supervoid, or even a simulation glitch? What if it's a fossile scar left behind by an ancient event that happened before our universe even began? This is the mind-bending proposal of the pre-Big Bang fossil hypothesis. To grasp this idea, we must journey to the frontiers of theoretical cosmology. Standard models teach us the universe began with a singularity, a point of infinite density, exploding outward in the Big Bang, creating time, space, and matter as we know them. But some scientists, unsatisfied with the notion of a true beginning, imagine something different, a cosmos with cycles, where universes are born, expand, collapse, and give birth to new realities in an endless cosmic rebirth. One such framework is the bubble universe model. In this scenario, our universe is just one bubble in a much larger multiverse, each bubble with its own beginning, its own physics. Sometimes these bubbles are born, grow, and then collapse, never maturing, into full universes. But their ghosts may linger, leaving imprints on the next cosmic generation. Some theorists, like Dr. Laura Massini-Horton, suggest that the cold spot could be the remnant of one such failed universe, a bubble that collapsed before ours began, yet left a mark in the very fabric of the space that would become irretrievable. When our universe inflated, this ancient void was stretched across billions of light years, its emptiness fossilized into the cosmic microwave background, a scar from before the dawn of time. The mathematics is daunting, but the logic is oddly poetic. During cosmic inflation, our universe ballooned at superluminal speeds. If there were traces of structure, temperature, or even energy differences left by previous universes, inflation would have blown them up to cosmic scales. A collapsed bubble utterly devoid of matter could have become the largest void in our observable sky. Its temperature would register lower, its structure eerily symmetrical, just like the cold spot we see today. This theory, though bold, is not without precedent. In the world of quantum cosmology, history can repeat in subtle ways. Quantum fluctuations in a prior universe might seed regions of emptiness or excess energy, surviving the transition from one cosmic epoch to the next. The cold spot, then, would be not just a window to the early universe, but a peephole into an existence before existence, memory written across the blankness, of course. The evidence is circumstantial, and the questions are profound. How do you prove the memory of a universe that no longer exists? How do you measure the echo of an event that took place before time itself had meaning? The cosmic microwave background, already stretched to its limits, offers only the faintest of clues, a subtle dip, a spot too cold, too empty, too persistent to ignore. For Dr. Roger Penrose, Nobel laureate and architect of the conformal cyclic cosmology theory, the idea is not so far-fetched. He proposes that our universe is but one in an endless succession, each leaving signals, faint concentric circles, or odd voids in the background radiation of the next. The universe, Penrose writes, may have memories longer than time itself, but even among those who study such possibilities, doubt remains. The fossil theory is audacious, nearly impossible to confirm, forever balanced on the edge between science and philosophy. Yet there is something haunting about the idea cosmic void not as absence, but as memory, older than everything we know. Interactive moment. Imagine you could send a message back to the time before time. What would you say? Would you ask what came before, or simply marvel that something, a whisper, a scar, a secret survived it all? If the cold spot truly is a fossil, then it may be the oldest thing we can ever hope to detect, a structure not from our universe, but from whatever came before. In its silence, it tells a story grander than galaxies, stranger than any science fiction, more humbling than any myth. As our journey continues, we must confront a difficult truth. The universe is not only what it remembers, but also what it forgets. In the next chapter, we'll explore what happens when cosmic history is erased, and how the cold spot might be a monument to the forgotten evidence that the universe itself is capable of memory and of loss. If time can leave scars, then perhaps eternity itself is written with invisible ink, its secrets waiting just beyond the edge of understanding. The universe is a storyteller, but not all of its stories survive. Across the cold expanse, memories fade, stars burn out, galaxies scatter. Even light itself stretches and thins until its message is almost lost. In this grand forgetting, the cold spot stands as both wound and witness, a place where the universe's memory falters, where something has been erased so thoroughly that only emptiness remains. What does it mean for the cosmos to forget? Physicists speak of entropy, the relentless slide from order to disorder, from clarity to chaos. Every process, every burst of starlight, every collision of galaxies leaves a residue of lost information. The second law of thermodynamics is the universe's way of telling us that nothing lasts forever, not even memory itself. Cosmic voids like Eridanus may be the ultimate repositories of this forgetfulness. Here, structure fails to form. Gravity never gathers enough material to ignite stars or shape galaxies. Instead, the laws of physics seem to stand back, letting silence and darkness prevail. In these vast regions, even the echo of creation, the cosmic microwave background, fades a little more, as if the universe itself is trying to scrub away what once happened here. The cold spot, with its profound emptiness, could be a kind of cosmic amnesia. Perhaps it's the remnant of a forgotten collision, a place where energy and matter were once torn away, never to return. Or perhaps it's a scar left by the erasure of some ancient event, a quantum fluctuation, a collapsing bubble universe now, overwritten by the endless expansion of space. Astronomers look for patterns in the data, seeking traces of what was lost. Dr. Joanna Dunkley, a cosmologist known for her work on the CMB, once mused, "There's a loneliness in these voids. It's as if the universe built walls around what it cannot bear to remember." Interactive moment. Have you ever looked at an old photograph and realized you no longer recall the moment it captured? Multiply that forgetting by billions of years and uncountable scales, and you have some sense of the cosmic oblivion that haunts regions like the cold spot. Yet, not all traces are truly lost. Sometimes, the very act of forgetting leaves a marker gap, a silence, a change in the pattern. In information theory, a missing piece is itself information. The dog that didn't bark, the note left unsung. So too, the emptiness of Eridanus may be telling us something essential, that there was once something here, now gone. Some theorists push the analogy further, imagining the universe as a vast, imperfect mind. In this model, voids are the forgotten dreams, the suppressed traumas, the places where reality itself has chosen to move on. The cold spot then becomes a monument, not to what is present, but to what has been erased, proof that even the cosmos is not immune to forgetting. The philosophical implications are staggering. If the universe can forget, what else might it choose to erase? Are there other voids, other scars, whose origins are lost forever? Secrets the cosmos keeps even from itself? Is forgetting an accident or a necessity a way for the universe to make room for what comes next? But perhaps forgetting is not always loss. In human lives, too, memory is selective. We forget pain, we move beyond sorrow, we let go of past selves to become someone new. Maybe the universe, in its own vast, impersonal way, does the same, clearing away what's no longer needed so new stars, new worlds, new stories can be born. The cold spot, then, might be more than a cosmic grave. It could be a space of possibility, a blank page where new history might one day be written. Its silence is not just the absence of memory, but the promise of what could still come to be. As we reach the edge of cosmic forgetting, we circle back to a haunting question. Is the cold spot simply empty, or has it been emptied, cleared out by forces, accidents, or events beyond our comprehension? What else, hidden by the universe's selective memory, waits to be found? In the next chapter, we'll challenge our assumptions even further. What if the cold spot isn't just a forgotten place, but an occupied one? Could emptiness itself be a mask, hiding something stranger than we can yet imagine? When the universe forgets, what stories slip between the cracks, waiting for curious eyes to uncover them? We are taught to fear the dark, to imagine that what is hidden is hostile or empty. But what if the darkest places in the cosmos are not voids, but veils, masks, behind which the universe keeps its deepest secrets? For decades, the cold spot has been seen as a cosmic nothing, an absence. Yet a growing chorus of scientists and dreamers is beginning to ask, what if it's not empty at all? What if something is hiding in plain darkness? In science fiction, voids are often imagined as hiding places for civilizations far older than our own. Ancient aliens building megastructures to cloak their activities, or using the voids as highways between galaxies, untouched by the noise of stars and dust. It sounds wild, but in recent years, SETI researchers have begun to take the idea seriously. The emptiest places, after all, are where you'd least expect to find life or to look for it. Could a civilization, harnessing energies on the scale of galaxies, create a dark patch so cold, so empty, that it would escape our attention? Some theorists speculate about Dyson spheres, massive shells that capture the light and heat of entire stars. But what if, on a truly cosmic scale, entire regions were engineered to be invisible? The cold spot could be, as one researcher put it, the universe's ultimate hiding place. But perhaps the truth is even stranger. In the language of modern physics, emptiness is never truly empty. Quantum fields ripple even in absolute darkness. Virtual particles flash in and out of existence, painting the vacuum with a frenetic, invisible energy. Could the cold spot be a kind of quantum cloak, a region where the rules are subtly different, where matter and energy cancel, where gravity curves not inward but outward, forming a gravitational hollow that swallows light and information? Some mathematical models predict that pockets of space can fold in on themselves, creating regions of negative energy or altered dimensions. Such a place would be invisible not because it's empty, but because it bends reality itself. Any signals sent into it, radio waves, light, even gravity, would be swallowed, redirected, or scrambled. In such a region, even time might flow differently. Interactive moment. Imagine standing at the edge of a cosmic abyss, knowing that on the other side, the rules of existence could be utterly alien. Would you try to peer in, or would you step back, wondering if what you found might change everything you believe about reality? A few scientists have dared to look, using sensitive radio telescopes and the far-seeing eyes of the James Webb Space Telescope. Teams are beginning to search for hints of something inside the cold spatter, flicker of unusual polarization, a whisper of exotic particles, a strange gravitational signature. So far, the darkness holds its silence, but that hasn't stopped. The questions from growing louder. What if life could exist inside a void not, as we know it, built of atoms and molecules, but as patterns in the quantum foam, structures woven from fields and forces? Life, in this sense, would be nothing like us, nothing we could ever recognize. Yet the idea is not impossible. Nature is a master of invention, and what we call empty could be teeming with phenomena beyond imagination. Others propose that the void is a doorway, a kind of cosmic backstage. In string theory and higher dimensional models, what appears empty in 3 dimensions may be rich with structure in others. The cold spot could be the shadow of a higher dimensional object, its true form hidden from our eyes. If so, we might never see what lies within, but its presence could still warp the fabric of our universe. As the search continues, some are moved not by fear, but by awe, to confront the possibility that emptiness is an illusion, that behind every darkness there is something waiting to be known as, to embrace the spirit of exploration that has always driven humanity. Whether it's life, a new law of physics, or a cosmic artist's invisible brushstroke, the truth behind the cold spot remains tantalizingly out of reach. Yet the greatest mysteries are often those hiding in plain sight, asking us not only to look, but to look differently, to see with new eyes, to question what we assume is empty, to believe that darkness can be as full as light. In the next chapter, we return to Earth, to the men and women who dare to stare into the void, building new tools, dreaming new dreams, and risking everything to uncover what might be hiding in the universe's plain darkness. Is the cold spot a mask, a mirror, or a message? And if so, who or what is waiting on the other side? Every age has its explorers. For some, the wilderness is a mountain or an ocean. For others, it's a mathematical equation or a scrap of ancient code. But in this era, the boldest explorers are those who dare to stare into the deepest darkness of the universe, those who refuse to be blinded by the comfort of the known, and who chase answers into the heart of the unknown. These are the men and women whose eyes dare to look into the void. We return now to Earth, where the story of the cold spot is not only written in cosmic microwaves and ancient photons, but in sleepless nights, relentless curiosity, and a refusal to accept easy answers. Young astronomers at observatories in Chile, Hawaii, and Spain calibrate their instruments with meticulous care, knowing that a single misstep could erase the faintest signal from the edge of understanding. Students hunched over glowing monitors squint at data that seems at first to be nothing but noise, searching for a pattern that might just change everything. One such seeker is Maya Lin, a doctoral student inspired by the iridinous void since childhood. As a teenager, she read about the cold spot in a popular science magazine. Now, she spends her nights using machine learning algorithms to sift through cosmic background data, hoping to tease out faint anomalies that human eyes might miss. For Maya and countless others, the hunt for meaning in the void is not just a job, it's a calling. Meanwhile, in control rooms far from city lights, veteran scientists like Dr. Istvan Shapudi and Dr. Joanna Dunkley gather their teams around. Streams of live data from next-generation telescopes. The James Webb Space Telescope, newly operational and peering deeper into the universe than ever before, is among their greatest hopes. Webb's infrared vision pierces the ancient darkness, mapping the faintest galaxies, and, perhaps, offering a glimpse into the very heart of the cold spot. What might it see? No one knows. The excitement is palpable, a mix of hope and trepidation. Will we find answers, or only more questions? Maya wonders aloud. What if we look into the void and see ourselves reflected back? This moment is a testament to the courage of curiosity. The void is not merely a physical gap, but a mirror for human longing and imagination. It's easy to stare into darkness and imagine monsters, or to dismiss it as meaningless. It's harder, braver to accept that what we find may append our ideas about reality itself. Interactive moment. If you could peer through the most powerful telescope in history and gazed straight into the cold spot, would you want to know what's there? Would you risk your certainty for a chance at something truly new? For many of these researchers, the risks are real. The quest for answers is a gamble with reputation, funding, and even sanity. Some colleagues rolled their eyes, muttering that time is wasted chasing after cosmic ghosts. But for the eyes that dare to look, the void is not an absence, it's a frontier. At international conferences, young astronomers trade rumors and theories in crowded hallways. Maybe the cold spot is a relic of a pre-Big Bang universe. Maybe it's a fingerprint from the multiverse, or the sign of a simulation's boundary. Maybe it's none of these. But no one can quite let it go. This hunger for discovery is contagious. It spreads from one generation to the next. Graduate students inspire high schoolers, teachers ignite sparks in the curious, and YouTube videos, like this one, sent minds wandering across billions of light years. The community grows, united by wonder, and as the tools sharpen, the questions deepen. New missions, ground-based and orbital, are planned to map the CMB and galactic structures with even greater precision. Artificial intelligence accelerates pattern recognition, drawing connections that were invisible before. The line between observer and observed blurs as technology amplifies our vision. Through all this, one truth endures: the void does not yield its secrets easily, but neither does it deter those who yearn to know. It's a dialogue, a call and response between silence and inquiry, between the universe's coldest places and the warmth of human curiosity. Perhaps, in the end, it is not about solving the mystery, but about learning to ask better questions, to become ourselves, the eyes that dare to look. In the final chapter, we reach the event horizon of knowledge, a place where answers fade into the vastness, and the void becomes a reflection of the greatest mysteries within us. What will you find when you dare to stare into nothing, and nothing stares back? At the edge of every known map is a boundary labeled unknown. Beyond that boundary lie dragons, monsters, and dreams. But beyond even those dreams lies something stranger still: nothingness itself. For centuries, humanity has feared emptiness, calling it void, oblivion, the abyss. But what if, in the heart of the cold spot, nothingness is not an ending, but a doorway to something greater than we can comprehend? Throughout our journey, we have explored every conceivable explanation for the cold spot in a. We've encountered cosmic scars, multiversal collisions, quantum anomalies, simulation glitches, and even fossils from before time began. Each theory pushes at the boundaries of imagination, science, and philosophy, yet all share one common truth: we simply do not know. And perhaps that is the point. Human beings fear uncertainty. We prefer tidy explanations, linear stories, predictable endings. But the cold spot refuses to grant us this comfort. It confronts us with the deepest truth of the universe, that mystery is built into its very fabric, that our cosmos, vast as it is, contains secrets it might never surrender. Standing at the edge of what we understand, looking into the silence of the void, we are forced to confront not just cosmic mysteries, but also the mysteries within ourselves. Why do we seek to know? Why are we driven to chase questions that may never be answered? Dr. Joanna Dunkley, reflecting on years spent staring into cosmic voids, put it simply, we search for answers because we're human, because knowing matters, but so does not knowing. It keeps us humble, curious, and alive. Interactive moment. When you look up at the night sky, are you comforted or overwhelmed by how much remains unknown? Does it make you feel small, or does it inspire or sense that you're part of something far larger than you can grasp? In the end, perhaps the cold spot isn't a place to fear, but a place to wonder. It reminds us that uncertainty can be a gift, a space for new stories, new questions, new possibilities. If every question were answered, if every mystery solved, the universe would feel smaller, more confined. It's the unknown that makes our journey meaningful. Maybe the void isn't empty at all. Maybe it's filled with everything we don't yet know how to see, waiting patiently for eyes bold enough, minds curious enough, hearts courageous enough to discover it. Young astronomers today, inspired by these mysteries, build new instruments that will peer deeper, farther, and with greater clarity. Future missions promise revelations we can't yet imagine. Technologies we consider impossible may one day open new windows, revealing secrets we haven't yet dreamed of, and each discovery will lead to new questions we cannot yet even conceive. And so, the cold spot teaches us that the greatest frontier is always just beyond our reach. It calls us not only outward to explore galaxies, supervoids, and anomalies, but inward to explore why we care, why we wonder, why we seek meaning at all. Perhaps the most important lesson of all is that we are not passive observers. We are participants, co-authors in the unfolding story of the universe. Every telescope built, every theory tested, every late-night conversation beneath the stars is part of this cosmic dialogue. The cold spot is not merely something to be solved, but something to be experienced, a testament to human curiosity, resilience, and imagination. So what lies beyond nothing? Maybe the answer isn't found in telescopes or mathematics, but in how the void changes us. Maybe the cold spot isn't hiding an alien civilization, a glitch, or even another universe. Instead mirrors our deepest desire to matter, to understand, to connect, to see our reflections not only in galaxies and stars, but in emptiness itself. And in that emptiness, maybe we discover our truest self-seekers, dreamers, explorers. Interactive moment. As you finish this journey, ask yourself, what does mystery mean to you? Does the unknown frighten you, inspire you, or both? As we step away from the cold spot, returning to our everyday lives, perhaps we carry its lesson forward. Embrace uncertainty, question boldly, and never lose the courage to imagine beyond the edge of knowing. Because somewhere, someone, maybe you, is looking at the sky and asking new questions. Perhaps you'll be the one to finally see clearly into the cold spot's heart, unlocking its secrets for the first time. Or perhaps, like generations before, you'll find new mysteries waiting just beyond your grasp. And perhaps that's exactly as it should be. If the universe has scars, the cold spot may be its deepest. But who or what left the mark? Subscribe if you believe the cosmos still speaks in riddles. And tell us, what do you think lies inside the coldest void ever found? Maybe your theory is the truth we've been waiting for.